let's talk about grid curves, and with the ultimate goal of computing surface areas of parameterized surfaces. So what I've set up here, let's say we have a parameterization which is given by these component functions that parameterizes some space curve in three-dimensional space. So this is attempting to visualize, let's say I want to find the surface area of some region here on this, well, maybe my exact number of dots don't exactly line up, but this is some bendy, wiggly portion of a surface in three-dimensional space, and I want to be able to compute its surface area. And the way that we're going to do that is by parameterizing it with this function phi, and then looking at the bounds of parameterization in terms of u and v. So let's say that for this parameterization, this corresponds to bounds that are from a to b in my u's and from c to d in my v's. Right? You can see how this translates, and of course this isn't necessarily, this is just a pictorial representation of that. The cool thing, or what we're going to look at, is thinking about, well, how can I represent the area of this little space right in here? That this, I'm going to approximate, it sort of looks like a rectangle, but a more accurate approximation is going to be approximation in terms of parallelograms. And the way that we're going to arrive at the direction of each of these vectors that define this parallelogram in three-dimensional space is by looking at how we transform these vectors under our I function. So for example, what happens if I hold my v coordinate constant and just think about a change in u? So I'm thinking about a vector over in this space, my change in u vector. When I hold v constant and look at my change in u, and it undergoes this transformation I to be able to get to wherever this function is over here, I'm going to call that my unit tangent in the u direction, or t sub u. Now this is the vector holding v constant. What happens when I take this vector and apply my I in order to figure out what the vector is on this parallelogram? Algebraically, t sub u really is just the partial derivative of my parameterization function holding v constant, so I'm taking my partial derivative with respect to u. Similarly, it's exactly analogous for my v's. So my t sub v is going to be the partial derivative of my parameterization function with respect to v, holding u constant. And now I have the magnitude of this little vector over here is going to be its direction, which is the partial with respect to u, times my little change in u amount. Similarly, this vector over here is my partial with respect to v times my change in v. Or, so if I want to know what is the area of this parallelogram, it turns out that the area of the parallelogram, I'll write this down, of parallelogram is going to be given by the magnitude of the cross product of these two vectors. You can pause this video and look at a review of how to find the area of I don't want to do it in this order. I want to do u first and then v. It'll just, because it's the magnitude, it doesn't really matter, but I want the notation to match the way that the notation goes in the book. It really actually doesn't matter. So the area of this approximating parallelogram, this tiny little area, is going to be the magnitude of this cross product, and I can discuss why in the other video. But notice that the magnitude of this cross product, I'll rewrite it like this, my tu crossed with tv times du dv. Oh, right now we're still approximating, so it's delta u and delta v. That's what that area is going to be. That we have a shorthand notation for the cross product of these two vectors, and I'll write it over here. That in fact, because both tu and tv lie on the surface of whatever this three-dimensional surface is, it means that the cross product of them are going to give you a normal vector. There, you can see my thumb. Or a vector that points out perpendicularly from the surface. And in fact, we're going to name that vector n. And as long as I take it in this direction, with u going this way and v going this way, it follows the right-hand rule, and it means that our n is going to be pointing up towards us, or a positively oriented normal vector. So if I wanted a shorthand way to write this, I could just write this as the magnitude of n, where n is the cross product of each of these unit tangent vectors. Delta u, delta v. That's the area of this tiny little parallelogram. But to find the area of this entire surface, we're going to take some limits, right? We're going to look at the sum of all of these little parallelograms, and we're going to look at the limit of those sums as the parallelograms get smaller and smaller. And that leaves us with our final equation for surface area. Well, it's going to be the magnitude of our normal vector, du, dv. As we take our limits, these deltas become differentials. And we're looking at the double integral of the bounds on u, where u in this case was going from a to b, and v was equal to c from c to d. And this is our equation for the surface area of this particular parameterized surface, where the bounds of the surface are given by these constant bounds. And of course, if we had functional bounds, we could use some of the techniques that we've seen previously. So that's some theory. So I want you to remember, what is this saying? This little piece in here is really just representing the area of one of the tiny parallelograms. And then we're just summing up all of those tiny parallelograms. And that's how we come up with our surface area. So next, let's go ahead and apply this formula to find the surface area of a cylinder of radius 2 and height 3. So the first step that we need to do is to parameterize this cylinder of radius 2 and height 3. And in this case, I think that the easiest way to parameterize it is to think of, notice that we have a fixed radius. The radius isn't changing as we draw this picture. This is my z, my x, my y. So my z values can change. I want my z values to trace out the heights down from 0 all the way up to z equals 3. It's just the way that I've set up this function. So I'm going to let one of my variables, v, be equal to my z component. And because we know what the bounds on v are, v is going to go from 0 to 3, because that's tracing out the height. I also could use the variable h if I wanted to. And then in order to get this circular behavior, we know that the radius is fixed constantly at 2. So I'm going to look at 2 cosine u, 2 sine u, because I know that that's going to trace out a circle of radius u, and that means the bounds on u are going to have to go from 0 to 2 pi to make it around in a full circle. So now I've parameterized this surface. In order to find the surface area, I need to find the magnitude of the normal vector. So I'm going to find t sub u, because that's my partial derivative of my parameterization with respect to u. That means that I'm going to hold v constant and take my derivative with respect to u. I get negative 2 sine u, 2 cosine u, and because I'm treating v as a constant, the derivative of a constant is 0. Next, my t sub v is the partial derivative of my parameterization vector with respect to v. So treating u as a constant, this whole thing is just a constant and goes to 0. And my v is 1. So in order to compute my normal vector, I need to take the cross product of my TU and TB, I, J, K, negative 2 sine U, 2 cosine U, 0, 0, 0, 1. So I get I times 2 cosine U minus 0 minus J times negative 2 cosine U, negative 2 sine U, excuse me, I misspoke, minus 0, plus K times 0, which gives me a vector of 2 cosine U, 2 sine U, 0. I almost missed the 0 there. And geometrically, this sort of makes sense. If I can think about it, I could plot points and say the 0 in the z component means that my normal vector is not going to be pointing up or down at all. It's just going to be pointing out. And as I move around the edge of this cylinder, the outward pointingness is going to change in a circle. And so that makes sense geometrically that my normal vector n is pointing out from the surface. Let's find the magnitude of n. That's equal to the square root of the first component squared, 2 cosine u squared, plus 2 sine u squared. So I can factor out a 4. Cosine plus sine is equal to 1. The square root of 4 is 2. That's a lot of work in my head, but you can verify that. But that was all of the hard part. Now we're ready to set up our integral to compute the surface area. Recall that we're going to use our bounds as u goes from 0 to 2 pi, as v goes from 0 to 3. The magnitude of n is 2, dv du. It's as easy as that. So what happens when we do this? Let's integrate with respect to v, and I get 2v evaluated as v goes from 0 to 3. We still have our du there. So that becomes 6. So now I'm integrating from 0 to 2 pi of 6 du. And that becomes, I'm skipping some steps in my head, 12 pi. And we can check this. Let's check with what we know about geometry. Well, what do we expect the surface area of the exterior of this roll of a cylinder to be? We think it should be base times height. In this case, the height is 3. So I'm checking. It should be 3, which is the height, times the circumference here, which is 2 times pi times r, right? Because it's the diameter times pi, which is 4 pi, which is actually 12 pi. Great. So we verified something that you could have computed maybe as an elementary school geometry student. But we can do it with some really fancy mathematics, right?